Hello, and welcome to our Acids and Bases pH meter video. First thing we had to do when working with the pH probe was properly calibrate it using a pH 7 buffer solution and a pH 4 buffer solution. To start, you must carefully remove the probe from its container and rinse with distilled water. Then you can place it in the pH 7 buffer solution and input that value into your meter. Next, rinse the probe again and put it into the pH 4 buffer solution, and then input that value into the meter. After that, you would rinse the probe again and place it back into the pH 7 buffer solution to test that it is properly calibrated. Finally, you would then rinse the probe with the distilled water and place it back into its container. By now, you're probably wondering, what exactly is a buffer? A buffer is a mixture of a weak acid and its conjugate strong base or vice versa, with significant amounts of both present in the solution. Buffers are used because when small amounts of strong acids or strong bases are added to them, the buffer can resist the pH change. When base is added to the system, the conjugate acid will neutralize the added OH- ions, generating more of the conjugate base. When acid is added to the system, the conjugate base neutralizes the added H+ ions, generating more of the conjugate acid. This causes the pH change to be very little since the amount of protons available in the solution did not change much. Now that you are fully calibrated and caught up, we can begin testing the different unknown pHs for common solutions. Proper technique for this is removing the probe from its container, rinsing it with distilled water, carefully putting the probe into the unknown solution, reading and recording the pH it gives, and then rinsing and rebottling the probe. While watching us test for the pH of several different solutions, I can explain to you the difference between strong and weak acids and what that means for equilibrium in a solution. An acid's strength is fully dependent on how much it dissociates in an aqueous solution. The stronger the acid, the more it dissociates into separate ions when placed in an aqueous solution. When an acid dissociates, it releases a proton to make the solution acidic, thus lowering the pH. This means that on a pH scale from 1 to 14, with anything below 7 being considered acidic, strong acids like HCl are going to have a pH closer to 1, whereas less strong acids, like acetic acid, their pH is going to fall more around 3-4. Strong acids fully ionize in an aqueous solution, creating a forward reaction resulting in all acid molecules being split into protons and conjugate base ions. Weak acids, on the other hand, do not fully break up and have a dissociated state, the conjugate base, and an undissociated state, the weak acid, that appear at the same time, meaning that only a fraction of the weak acid's protons are donated. This creates a dynamic equilibrium equation where the rate of dissociation and the rate of formation of the weak acid are equal. Since we now know the difference between weak and strong acids and have used the probe on all solutions, let's take a look at the values we found for each solution's pH. Now that we have collected all the pH data for each of our different acids and bases, we must properly clean up. This includes pouring the solutions down the sink with water, washing and drying all glassware, rinsing and putting up the pH probe, and wiping down the workbench. Thank you so much for watching our video, and we hope you learned something along the way.